well, remember that we had a linear transformation from one vector space V to another one, say W. Oops. So it's a linear transformation. Yeah, so before I'll continue, so this is eventually theorem 7.9 of the lecture notes, 7.9 of the lecture notes. And what do we have? Well, we have, on the one hand side, we have the so-called kernel of this linear transformation. Yeah, so it consists, well, let me remind you that this one just consists of all vectors from V, so that T maps those vectors to 0 here, okay? So another way to say this kernel is the preimage of 0. So it's a kernel, it's one subspace of V. And then there's another subspace of W, which is the so-called image of T. So let me also remind you that image is just, well, it consists of all vectors that are actually coming from V, right? So it's also, well, and as we all know, this is also a subspace, but now of W. Yeah, so whenever one has a linear transformation, there are always two subspaces which are coming with it, namely the kernel and the image. And well, what do we want? We want to relate the dimensions of those subspaces. And well, there's a following fact. So whenever we have such a situation here, then, well, so of course we assume that if V is finite dimensional, well, then we have the following nice formula, namely the dimension of the whole vector space V coincides with the sum of the dimensions of the kernel of this subspace and of the image of that subspace. And this is a so-called dimension formula. So you see it relates three integers, right? Each of them is a dimension of something, of some subspace or vector space. Well, there's some notation. Well, sometimes, so this one is called, well, this number, the dimension of the kernel, is called the nullity of T. And sometimes it's also denoted in this way. And well, this integer, this number is indeed, well, it's called the rank of the linear transformation. It's called the rank of T, and it's denoted by rank of T. Basically, what this formula again tells us is that the nullity of T plus the rank of T equals to the dimension of the domain. Yeah. Let me give a proof. Well, first of all, as I said already, both the kernel and the image are subspaces, right? And it's also clear that since V is a finite dimensional, then of course its kernel is also finite dimensional, right? So, well, so that we can choose a basis. As a first step, what we do, we choose a basis of the kernel of this subspace. And well, well, we need, well, let's say, suppose that those vectors U1, UK, they form the basis of that kernel. Okay. Well, maybe, yeah, perhaps it's good to denote it by some letter. So say S prime is the basis. is the basis of ker of t. Okay, now what we know, well, we know that such a basis can be extended, right? Because look, I mean, this is a subspace of our vector space, right, V. And so we have a subspace, we have a basis of the subspace, and we all know that any basis of any subspace can be extended to the whole basis of V, right? So what we now do, we extend the basis S prime to a basis, well, say, okay, so we start, of course, with U1 to UK, sorry, and then we add extra vectors, right? Because there should be more vectors, so you just continue like writing UK plus 1 and so on up to, okay, so we need some notation for the dimension. Well, suppose that the dimension of V is n, just denote it like this, and then of course the last vector should have the index n, so there are precisely n vectors. So you see, we extended those vectors to the basis. And well, let's denote this basis by S of V. So we can always do this, right? Now, well, since T is a linear transformation, it satisfies several standard properties, right? We all know those properties. Namely, well, in particular, what we can do, we can just, well, suppose that we are given a vector. So any vector V from the image of T can be written as, well, let's just write it. So V is, so it's from the image, right? So it's an image of some other vector. So it comes from some other vector, say U. Yes, because V is in the image, so we can always write it like this. And then what we do, well, look, I mean, so this is a basis of our vector space V. So we can write any vector U as a linear combination of vectors from the basis. So we just do it. So T of, and here we just write a linear combination, A1, U1 plus, so just take these vectors here, A2, U2 plus up to the very last one, AN, UN. Again, any vector U we can write down as a linear combination, right, of the vectors from the basis. And so, well, what we can do next, since T is a linear transformation, we can expand it. We can expand this. We can open the brackets here, right? Because, well, we all know that, so T is a linear transformation, so we can just write it as A1 times T of U1 plus A2 times T of U2 plus, and so on, plus AN of T of UN. Yes, okay, but on the other side, well, let's just carefully write down. I mean, this is a long sum. This is a long sum, and it has n summands, right? But look, I mean, it consists of this part here and of that part there, right? So let me carefully write it down. A1 T1, A1 T of U1 plus AK T of UK. So that's a first part corresponding to this basis vectors. And then the remaining part is just AK plus 1 T of UK plus 1, and so on till the very end, AN T of UN. Okay? And then, well, remember that these guys here, those vectors here, those vectors, they form the basis of the kernel, right? So in particular, each of those vectors belongs to the kernel. So what does it mean? It means that if we apply T to each of those vectors, we will get 0. right? So let me write it. So let me substitute. So indeed, in this sum, what do we have? We have this one is 0, this one is 0. All vectors in this part, they're just trivial, they're just zeros. So we'll just get that this expression equals to this expression, ak plus 1, t of u, k plus 1 plus, and so on, a n t of u n. Okay, or another way to say this, well, another way to say this is just that a vector v can be written as a linear combination of those vectors t of uk plus 1 up to t of un. So let me write it. So v, so we just showed that v belongs to the linear span, right? To the linear span of those vectors. T of uk plus 1 up to t of un. But look, I mean, but what's that? Well, look, I mean, so v is a vector from the image, right? And we, of course, we just do this for any vector from the image. So it means that the image indeed sits inside that span, right? We can realize any vector from the image as a linear combination. So it sits inside this span. But on the other side, each of those vectors, tk plus 1, tun, they already sit inside the image. So the span has to be inside the image, right? So what we just showed is that image is contained in the span and span is contained in the image. So meaning that they two coincide. So this implies that the image of t coincides with the span of those vectors. T of uk plus 1 up to t of un. Okay? Good. So now, well, what we claim is that, so now we know that the image, how to describe the image, so it's a linear span of those vectors. Now what I claim, now what we would like to show, we would like to check that those vectors are indeed linearly independent. So let me do this. That those vectors, this subset, this set of consisting of t of uk plus 1 up to t of un is linearly independent. So why is it so? Well, okay, so, well, let's just use the standard criteria. So let's just form a linear combination of those vectors, set it to be 0, and then, well, check whether this can happen only for 0, well, when all the coefficients are zeros, right? Okay, so let's look at the following. Let's take just a linear combination, ck plus 1, some scalars, uk plus 1 plus cn t of un. And then let's just set it to be 0, okay? And then see what will happen. Well, okay, if you set it to be 0, then what we can do with the left-hand side, well, we can actually put all the scalars and the sum inside the bracket. So we can just write it, well, because t is a linear transformation, you can also write it like this. So ck plus 1, uk plus 1, plus, and so on, plus cn un, right? You can always put it inside the bracket. And then what do we see? We see that c, when we apply t to this vector, to this linear combination, we get 0, right? So, well, if we just denote this vector by u, yeah, then what do we get? Indeed, yeah, what do we get? Well, we just obtain that this vector ck plus 1 uk plus 1 to cn un, well, it belongs to the kernel of t, right? Because look, I mean, if we apply t to this vector, we get 0. So this guy must be inside the kernel. Yes, but on the other side, since, well, look, I mean, since, what is S? Remember this basis that we obtained, right? By extending the given basis as prime. So what is S? Well, S is just extension, right? S prime, and then union the rest, the remaining vectors. So let me write it this way, S without S prime. And we also know that this is a basis, right? And also we know that, well, these two subsets are disjoint because it's an extension, so they're different, right? So S prime intersect S without S prime is empty. So they're disjoint. So what do we know about this situation? Well, what can we conclude from this is that, well, in this case, our vector space, right, this is a basis of V, and then we sort of subdivide this basis into two, right, subsets, and they disjoin, so we can take those, the spans of those subsets. So we get two linear subspaces, and then one of the properties of the direct sum is telling us that this is just the span of the first and direct sum with the span of the second. So let me write it here of T, because we already know that this is a span of those, right? Plus the span of the remaining uk plus 1 un. Okay, and in particular, we also know that the kernel of T intersect the span, the second linear subspace, is a trivial subspace, is trivial. Okay. Well, but then look, I mean, well, we'll just come back to this vector. So it's on the one hand side, it is in the kernel, right? That's what we just showed. But on the other side, it's also in the image. I mean, this was on the previous slide. Yeah? So meaning that this U belongs to the intersection, belongs to this intersection here. So it has to be 0. Yes, so it has to be 0. And what it means? It means, so this is a 0 vector, right? And this is a basis, right? And so all the coefficients then, they have to be zeros, right? I mean, all this, well, again, I mean, those vectors are linearly independent, uk plus 1 to un. So u is 0. So by the very definition, all those coefficients must be trivial. And therefore, all those coefficients, they have to be zeros. Okay. So, right. So basically what we just checked, well, let me again look at the previous slide. So what we just checked, look, I mean, we checked that the image is this linear span. And on the other side, this is linearly independent. So meaning that those vectors, they form a basis of the image, right? Now we combine all these facts together. We combine all this knowledge and get the following. Okay, so, well, so we just concluded that this is a basis T of un is a basis of the image, right? Because we showed that it's a span of this is an image and they're linearly independent, so it's a basis. Now, if you want to get the dimension formula, we just count how many elements are there in the basis, right? Okay, so well, the dimension of V then equals, so this is the number of elements in where? In S, right? And that's clearly is just what? It's a dimension number of elements in S prime. And that's precisely the dimension of the kernel, if you remember, plus, well, the complementary number. So it's a number of elements in S without S prime. And that's precisely the dimension of the image. Yeah, because this set is exactly, so this number here is precisely the basis. So you see how many, okay, so let me maybe mention, so this is K, right? And this is exactly N minus K. How many elements are there? So N minus K, right? So this basis is N minus K elements, and S prime, as we know, this has K elements, and the sum is just N. And this finishes the, so let me state it as a corollary. Okay, so now, well, let's look at the linear operator C from V to itself. Let C be a linear operator. A linear operator. On a finite dimensional vector space. Well, then the following conditions are equivalent. Okay, A. Well, T is injective. Again, let me remind you what's injective. Injective means that the kernel is zero, right? The kernel is trivial. The kernel is a zero space. Or if you wish that this is one-to-one. We already have seen that this is the same, right? So now B. T is surjective. Yes, that's amazing in the sense that whenever you have a linear operator, to be injective is the same as to be surjective. And of course, if it's injective and surjective, then it's C. C is bijective. Okay. So indeed, this is an immediate consequence of the previous formula, and the proof, as I said, it's pretty straightforward. So basically, we just need to, how to check it, apply the dimension formula. Well, okay, so let me again write it down. Dimension V is the dimension of the kernel plus the dimension of the image, right? So for instance, how do we see that A is equivalent to B? Well, suppose that T is injective. Suppose that T is injective, okay? Then what does it mean? Well, it means that the kernel is zero, right? So it means that this dimension is zero, right? But then look, then the dimension of V will coincide with the dimension of the image of this linear transformation, right? But that precisely means that V coincides with the image as a subspace. So, and this is exactly means that T is surjective. In the other direction, if T is surjective, then this number is, if T is surjective, then this number is just N. I'll suppose this is N. If T is surjective, then this dimension, this image of T coincides with the V, right? By the very definition of surjectivity. So this number is just N itself. So of course the difference N minus N gives you zero here. So meaning that the kernel is zero. So it means that T is injective. So that's kind of clear, right? And finally, of course, as I mentioned, if it's both injective and surjective, then of course it's bijective. So this part is easy to see, that A is equivalent to C and B is equivalent to C is easy. Okay. So why this corollary is useful? Well, it's because it gives a nice criteria. Say, for instance, if you ask to verify whether a given linear operator is injective or surjective or bijective, right? You can easily apply this. You can see that it's okay. Right. Is there any question? It's a story about linear transformations. And matrices. Okay, so right. So eventually, you have seen it already, perhaps, in the linear algebra class at the very, very end of the first year linear algebra, where those linear transformations and matrices were defined very briefly at the very end, probably. So basically, the idea is, so you have so what you need? Well, you need, of course, two vector spaces, V and W, and then you need a linear transformation from V to W. So it's a linear transformation. And of course, you need to assume that both this V and W are finite dimensional. And why we need to assume this? Because in order to proceed, what we need to do now, we would like to choose a basis. We would like to choose actually two bases, one from V and another one from W. So assume that, say, V has a basis, and we need a finite basis. A basis, say, well, let me use a Greek letter to denote a basis. So it's alpha, and that's a basis of V, V1 to Vn. And say W has a basis beta, which is, well, so it consists of vectors W1 to Wm. Okay, so again, I mean, given two vector spaces, a linear transformation, we need to choose two bases, one for V and another one for W. And after we did so, we can do the following. After we did so, what we can do, we can just write each vector. So each vector V from V, then can be written as, well, we just write, okay, V as linear combination of the elements of the vectors from the basis of V, right? So here A1 to, say, AN Vn. Again, because this is a basis, maybe I should use this calligraphic V. Yeah. And so moreover, since this is a basis, this expression is unique, right? We already have seen it. So whenever you fix a basis, then any vector can be written uniquely, in a unique way, as a linear combination of the elements of the vectors from the basis. Can be written, say, let me put uniquely. And, well, let's see what will happen with this linear combination after we apply our linear transformation to it. Well, what is T of V then? Well, T of V is then T of A1 V1 plus and so on plus AN Vn, right? And since T is a linear transformation, we can expand, we can open this bracket. So what do we get? We get A1 T of V1 plus AN T of Vn. So that's kind of easy, right? We already have seen it before. Okay, so what does it mean? What does it tell us? Well, it tells us that any linear transformation is indeed uniquely determined, so it's uniquely determined by its values on the basis vectors, right? Again, so any linear transformation, so T is uniquely determined by its values on the basis vectors. By its values, well, I can even write it TV1, CVN. Yeah, so in order to describe, to define a linear transformation, you can just say what are those values, right? And then you can restore any other value, like using this formula, using this presentation. Okay. Now, well, what we can do, so we kind of memorize this fact. Okay, what we can do next, well, we can just say the following definition. So for each of those values, say TV1 up to TVN. Now, remember that those guys, they now sit in W, in the codomain, right? And remember that for codomain, we also have chosen a basis. So we'll have another basis, beta, right? So we can do the same story. I mean, we can express, so for each such vector in the codomain, so let T of Vj, so just choose one of those with the index j. So T of Vj be the following. We can, of course, express it as a linear combination of vectors from beta, vectors of the basis of W, right? And let me denote it like this. So I write I use a double index. So J reflects that we apply it to this vector. So A1J of what? Of W1 plus A2J of W2 and so on. MJ of WM. So again, for each of those values, we express it in terms of the basis beta. And we call the respective coefficients by A1J, A2J, and so on, AMJ. Remember that all these coefficients are, say, A1J and so on, all coefficients that appear here, they're all from the field of coefficients F. They're taken from the field of coefficients. Okay. And again, of course, this expression is unique. So be a unique expression. In terms of beta. Okay. Now, what we can do, well, look, I mean, we can also write all these coefficients as a table, right? Because they are already kind of given as a table, right? If you think about the first index as a number of row, and the second index is a number of column, and at the position, say, ij, we put the element aij, what do we get? We get a table, or we get a matrix, right? So let me say this. So we write aij, so where I runs from 1 to m, right? So that's the first index. You see the first index from 1 to m. And the second index runs from 1 to n. That's the second index. So it's taken from here. So it's n. So we write aij's as m by n matrix. Well, just this one, A11. Okay, so there are m rows AM1. Here we write A1N, and here we write AMN. And there are some Aij, which is the ith row at the intersection of ith row and jth column. Yeah, so we can write all these coefficients like a table, like a matrix. And so this matrix has a notation. So let's denote it like this. We put C because it comes from the linear transformation C, right? And of course, it also depends on the basis alpha and beta, right? Because when we choose those coefficients, you see, we use those basis vectors here for beta and before for alpha. So of course, this matrix will depend on the choice of the basis for V and for W. So that's why it makes sense to denote it like this. So this is this matrix. Well, right, we need a name for this. So this matrix is called, so this M by N matrix is called the transformation matrix. Of the linear transformation C with respect to the ordered bases. Bases alpha and beta. Why I put the word ordered? Because of course the order here does matter, right? I mean, because whenever, I mean, we have to fix the order of basis vectors so that we will fix the rows and columns, right? Okay, so that's why I put here the word ordered. Okay, so yes, so so in this way we get a transformation matrix of a linear transformation. Yes, and well, now let me just, I mean, what I'm going to do, I'm going now to state a couple of properties and then give examples. So, but before even stating the properties, let me also introduce another notation, like a simplified notation. For instance, sometimes it can happen that V is just the same as W. Say, for instance, you have a linear operator, right? Then V coincides with W. So, and in this case, also it can happen that there's only one, so there's only one basis that you choose and say alpha is the same as beta. Okay, so then in that case, it makes sense to denote such a matrix but just simply by T alpha. So you see, I don't write beta. So basically it means that we are dealing with linear operator and we choose just one basis. So beta is the same as alpha. Okay. Now, well, sometimes if the basis is kind of fixed, like for instance, if we are talking about Rn, a linear operator on Rn, and we choose a standard basis. So whenever we're dealing with a standard basis, so alpha and beta just coincide with a standard basis, then we can just write simply by T in the brackets. Then the transformation matrix will be denoted like T in the square brackets. So in this case, it means that, so this is linear operator and the standard basis with respect to the standard basis. Okay, so that's a common notation for such transformation matrices. Well, now let me, as I promised, I would like to state a couple of properties. Okay, and the first property is the following lemma. So suppose we have, say, linear transformations T1, T2, and C from V to W. So B linear transformations. And suppose also that C is some chosen constant, some fixed constant. Well, then we have the following. Well, of course, we can take, well, let's take T1 plus T2. We can do it, right? Because it's a T1 and T2 are functions, so we can take the sum of functions. We can already, well, we have seen it already, right? How to do it. And this, of course, gives us a new linear transformation. And one may wonder what will happen with the transformation matrix of it. Well, in this case, what will happen is that, okay, so we need also to choose alpha and beta, of course, the bases, right? In this case, the transformation matrix of the sum with respect to the basis alpha and beta is the same as the sum of transformation matrix, the actual sum of matrices. So it's like we are given two matrices and we just add them like in the usual way. Just add the respective entries, right? Okay. And well, say suppose that we have a T and we would like to look at the scalar multiple of this linear transformation of this function. One may wonder what will happen with the matrix. Well, but then the matrix is just C times the matrix for the original T. So let me concentrate more on examples. Okay. Right. So there are, of course, a couple of trivial examples, namely, well, let's just look at this map, say T from V to W. And well, let's suppose that this is a zero trivial map or zero transformation. So what does it mean? It means that T of V is set to be zero for all V. What will happen with the transformation matrix then? Well, in that case, you can choose any basis of V of W, doesn't really matter. You can choose any basis. I mean, since this is a zero, all the coefficients, I mean, when you take a vector and expand it in terms of the basis, I mean, it's when you expand the value of a vector in terms of the basis, since the value is zero, all the coefficients are zeros, right? So meaning that this is just the zero matrix. So it's a matrix where all entries are zeros because all coefficients are zeros. This is kind of trivial example. Well, there's another easy example. Well, now, so what's the next sort of, what's the next map we should take? The easy map. Well, of course, there's this one. Well, let's take V. Let's take the same V, and let's take the identity map. Identity. So what it does, let me remind you, well, basically it just sends any vector to itself. So it does nothing. Then what will happen with the coefficients? Well, okay, you can choose a basis, say, well, let's choose, say, alpha is beta. So here's alpha, here's beta, and it's just the same basis. Okay, then, well, you can see easily that if you look at the transformation matrix, then what's that? Well, so let's pick up a basis here, basis vector here, say, I don't know, say, ith basis vector. Where will it go? Well, it will go to the same basis vector, right? So meaning that if you order the basis, so from 1 to n, say, right, then each basis vector will go to the same basis vector. So in this case, the only coefficients which will appear, that's the coefficients on the main diagonal, right? So because it's 1 goes to 1, the first goes to first, second goes to second, third goes to third. So each coefficient will be on in the position I comma I, where I is just a row or column, right? So it's the same. So it's a diagonal. It's a main diagonal. And what's the coefficient? Since the vector goes to the same vector, the coefficient is 1. So the answer is this matrix is, in this case, is just this matrix where you put ones on the main diagonal and zeros everywhere else. So this is a so-called identity matrix. Again, for this example, it's essential that your second basis, beta, coincides with alpha. So it has to be the same basis. Okay. Now, what's the next? Well, the next example, well, let's look at the so-called stretching map. So let me remind you, so what's a stretching map? It's again a linear operator from V to itself, okay? And well, again, I choose alpha is the same as beta, the same basis for both copies of V, yes? And our stretching map just does the following. So it sends a vector V to its scalar multiple for a fixed C, non-zero C. Okay, then what will be the matrix? Again, by the very similar reasons like here, well, the only difference is that if you're given a basis vector, it will be sent to its C multiple, right? So the only difference is that the matrix that you will get will just have C's, these coefficients, on the main diagonal and zeros everywhere else. So another way, well, this is just a multiple of the identity matrix, C multiple of the identity matrix. Well, sometimes the identity matrix is denoted by I. So this is the identity matrix. So in this case, it's just C times I. Okay, now let me give a little bit more concrete example. So, well, let's look at the rotation. So now our vector space is just classical R2. And we have the same copy of R2. And our linear transformation, what it does, it rotates. It rotates our plane around the origin by the angle, say, theta. So T is the rotation of R2 around the origin 0, 0 by theta, by the angle theta. Okay, so now, well, okay, so let's fix a basis. So here we would like to fix alpha and the same beta. And this is just, well, let's pick up to be the standard basis. So namely this one, 1, 0, 0, 1. Of course, we can choose a different one, but then the answer will be different. In this case, what will happen, so here's a rotation is taken counterclockwise, okay? In this case, the matrix will be, you see, I don't write alpha here because it's a standard basis. So then the transformation matrix will be just this one. You can recognize it probably. So cosine theta, sine theta, minus sine theta, and cosine theta. Those will be the coefficients. So this is a so-called rotation matrix. And so on. So indeed, of course, any linear transformation in finite dimensional vector spaces can be written, can be represented as a matrix, depending on the basis. Right? Let me again stress that the presentation, of course, depends on the choice of the basis. If you choose a different basis, then the matrices will be different because the coefficients will be different. Okay, so now let me sort of summarize it perhaps by stating the following theorem. So let V be a vector space. finite dimensional vector space. So finite dimensional over a field F with a field of coefficients F, and let alpha be its basis. We choose a basis of V. Then what we can do, well, again, we can look at all linear operators on V with alpha is the same as beta. It's all linear operators. We know that this forms a vector space of linear operators with respect to the usual addition and scalar multiplication. Yes, and so this was denoted by L of V, if you remember. So it's a vector space of linear operators. So it's a vector space of linear operators. And basically what we just discovered is that to any such a linear operator with a fixed alpha, and this will be, of course, say if n is a dimension of V, this will go to the, each such linear operator would give us n by n matrix. So let me write it n by n matrix. So it's a set of n by n matrices. Again, so this is a space, this is a vector space, this is also a vector space, we all know this, right? And so the claim is that, so let me write it, so maybe I should denote it, let me denote this correspondence by rho alpha. So what this correspondence does, well, just to each linear operator, associate its transformation matrix. Okay, so again, this is a map, this is a function from this space to this space, from this vector space to this vector space. And what's the claim is that, the claim is that, so let this be a function, then rho alpha is a linear transformation by itself and what is more important, rho alpha is bijective. So in other words, each matrix would correspond to a linear operator, and each linear operator would correspond to a matrix. There is a one-to-one correspondence between matrices and linear operators, right? Again, I would like to stress that this correspondence between matrices and linear operators depends on the choice of the basis alpha. If you choose a different basis, then the correspondence will be different because the coefficients will be different. Okay, so now, well, let me check it. Let me prove it. Okay, proof. Okay, so matrix is a linear transformation by itself, linear transformation. Why is it so? Well, to check that something is a linear transformation, one has to verify two properties, right? That it preserves the vector addition and the scalar multiplication. Nice, but look, I mean, okay, what will happen if we apply this to the sum of two linear transformations? Well, but then look, I mean, this is what? By the very definition, this is this transformation matrix, T1 plus T2 alpha. That's by the very definition. But then by the lemma before, we can expand it, right? We can open these brackets and write it as a sum of the respective transformation matrices. And well, that's precisely what we want, because this is rho alpha of T1 plus rho alpha of T2. Yes. So in other words, this map, this function preserves the vector addition. And the similar story holds for the scalar multiple. So rho alpha applied to CT, what's that? This is by the very definition, this is CT alpha, this transformation matrix. And again, we can use a property of the transformation matrices, because this is just C times T alpha. And so this is C times rho alpha T. So our function, our map, preserves the scalar multiplication. So rho alpha is a linear transformation. This is done. Now the second part of the story is to show that this is a bijective. Okay, let me also introduce some notation. The map, which is a linear transformation and bijective, sometimes people call it an isomorphism, linear isomorphism. Let me put linear here, linear isomorphism. Okay, so to show the second part, to show that it's bijective, well, what can we do? We can use the dimension formula, right? Remember, there was a dimension formula and the consequence. And in particular, it's enough to show, well, even not the dimensions, or okay, let me just check. Okay, so bijective is what? It's injective plus surjective, right? Okay, let's say see why it's injective. Let's see why it's injective. So basically, we just need to show that the kernel of rho alpha is trivial, right? Why it's a trivial? Why it gives us a zero linear transformation here? Why is it so? Well, okay, so let's suppose that rho alpha of T is 0. So again, what is this 0? This 0 is a zero matrix, right? Because that's what does it mean to be 0 in the vector space of n by n matrices. So suppose that rho alpha of T is 0. So this is a zero transformation matrix. But then look, well, what does it mean? It means that all the coefficients are zeros, right? When you expand in terms of the basis vectors, when you expand it as a linear combination of basis vectors, all the coefficients must be zeros, right? So in particular, say T of Vj, if you remember, that was A1j, say V1, right? Yeah, so W1 plus and so on, plus A MJWM, right? And so on. And so all these coefficients, they have to be zeros, right? So this has to be 0, okay, for each basis vector. But it means that the map itself is a 0 map, right? Because it sends each basis vector to 0. And in particular, it sends its linear combination to 0 as well. So it sends any vector to 0. So then it means that T is the 0 map. But that's exactly what we want, because we want a kernel to be consisting only of the 0 map. And that's what it is. So the kernel is 0, so the map is injective. Now, to see that this is surjective, well, look, I mean, basically what we ask to do is given a transformation matrix, any matrix, you just write any table, you would like to construct out of this a linear transformation. But look, I mean, what's this transformation matrix is telling us? Well, it gives us the table of coefficients when we express a vector and the value of a basis vector in terms of the basis, right? And so we know that the linear transformation is uniquely determined by its values on the basis vectors. So indeed, given such a matrix, we can just write, okay, we can just write T of Vj to be this, where we put instead of A1j and AMJ our coefficients. So meaning that each matrix gives rise to a certain linear transformation, which is defined like this. So it means that this map rho alpha is surjective. Yeah? So any matrix comes from such a linear transformation. So it's injective and bijective, meaning that it is indeed injective and surjective, so meaning that it is bijective, and so it is an isomorphism. Okay, so that's a key property. Right, so let me again stress that this property is just telling us that there's kind of, whenever we want to study linear operators with a fixed basis alpha, then this is just the same, this is equivalent, you can express it in terms of the matrices, right? M, N, F. So it's N by N matrices. So if I'm given a linear operator, I have the associated matrix. And if I'm given a matrix, I have the respective linear operators. So this is very useful. Why? Because if you ask a question in terms of the matrices, you can translate it immediately in terms of the linear operators just by taking the respective linear operators, or other way around. If you have a question about linear operators, you can translate it in terms of the matrices. Yeah? After, of course, fixing the basis alpha. Okay. So, right. So let me maybe mention the last property of the transformation matrices. So it's again this lemma, which again I'm not going to prove it. It's just a nice exercise. You can find it in the lecture notes. So now suppose that we have two linear transformations, T1, V1 to V2, and C2 from V2 to V3. So now we have three vector spaces. One linear transformation goes from the first to the second, and another one goes from the second to the third. And that what we are interested in, in its composite. The composite then will go from V1 to V3. Again, those are linear transformations, so they're functions, right? And here we're just taking the composite of them as functions. So just apply one after another, okay? Now, of course, if we want to deal with matrices, we have to fix a basis. So alpha, beta, say here's beta and here's gamma. So we need now three bases, right? Three bases, alpha, beta, gamma. And then what this property is telling us that if you want to compute the transformation matrix of the composite from alpha to gamma, then this is the same as the product, as the multiplication, as the product of matrices, of the corresponding matrices, T2 of beta gamma times the usual matrix product, T1 of alpha beta. So this is also a nice formula, which tells you that indeed the composite of linear transformation just tells us that the composite of linear transformations corresponds to the product of the respective transformation matrices. So again, the proof is an exercise. So you can also find it in the lecture notes. So just you apply the definition, you take the basis vector, you expand it, in terms of another basis, and you substitute and then expand it again. Okay, and maybe just a consequence of this fact that, of course, since we are dealing with composition of functions, and some of the functions can be invertible, right? Say bijective functions are invertible, so there's an inverse. So let me say that let T be a linear operator, an isomorphism. So it is bijective, and we fix a basis alpha there, here and there, the same basis, okay? And then, well, let's look at the respective transformation matrix. One may wonder, what's the transformation matrix of the inverse? Again, so this is an isomorphism. So this is the bijective function. So there's the inverse, right? And we know that the inverse is again a linear transformation. Okay. And so, well, then the claim is that, well, if you want to compute the transformation matrix of the inverse, well, this is what? This is just the inverse of the respective transformation matrix of T, the usual inverse. Yeah. Again, be careful that, so here it's the linear operator. So the dimensions are the same, and we fix just one basis alpha, right? Okay. So how one gets this consequence? Well, you just substitute. I mean, you just take this lemma, take V1 to V2 to be equal to V3. All bases have to be the same, just coincide with alpha. And take T1 to be T, and take T2 to be T inverse. And then, of course, you will get, what do you get here? T composed with its inverse gives you the identity, right? This is the identity matrix on the left. And on the right, you will get T times the inverse of T, or other way around, T inverse times T. Yeah, and that precisely